Hello everyone, welcome back to ECE350, lecture 19. Today we're going to talk about general relationship between H and E, as well as we're going to try to solve some problem when you come back to the class. So normally K is in Z direction over here and E is in X direction. That's what our direction from the beginning. So if I do K cross E, I'll get positive Y right here, right? In the Y direction. And if I do K cross H, I'm going to get negative X direction right here, okay? So that is a basis for this one here. H, the magnetic field, which is in the Y direction, is the result of E with the magnitude 1 over eta times K direction, right? And for the E, who's in the X direction, so it's a negative X direction over here. That's why negative on this side over here. Then is a eta, which is a constant, and times K cross H, right? So this is the common relationship between magnetic field and electric field in the wave propagation. Okay, now up to this point, we assume that we have E in the X direction, Y in the H in the Y direction. But it might be very realistic that your E could have both X and Y component and H could have both X and Y component. So if your E has both component X and Y, so E is over here, X component, Y component, right? Both are propagating in the positive Z direction, right? So then how do you get the H from here? So we know that in the previous slide that this would be H cross E, right? So sorry, H, not Z cross E, right? So Z cross E. So first component is X. So Z cross X will give you positive Y. So this positive Y here, that's why you can see that this X component came here, right? Then Z cross next is Y. Z cross Y will give a negative X right here. That's why your Y component came to that. So H is basically negative X had EY positive Z in the positive Z direction over eta plus Y had EX positive Z over eta. So these are the two very common expression for E and H, which has the both X component and Y component. So that's basically over here. So this is your H, this is your E, and H has two components here. This is your HX right here, right? This is your HY right here. So that's what showing what here, HX, HY. All right. All right. We're gonna do some simulation in the class to show you that how it moves. All right, and same in the time domain. We're gonna do that too. So one of the application, as I said in the beginning, of this wave propagation is the RFID, radio frequency identification tags, right? You can see the tag. Sometimes you go to farm, you can see the tag at the ears of cows. Also, you use the tag in your tool booth and many other places, right? How does it work? So it has two different components. It has a tag and it also has a tag reader. Tag reader is basically both receiver and transmitter. So when your tag comes close to a tag reader, so tag reader transmit a signal. So that signal goes to the tag, and tag could be both passive and active. Let's talk about the passive one. So goes to the tag. Tag has a coil. So that gets the signal from the tag reader. That signal strong enough to produce a current into the tag. That current activate the chip on the tag reader, and then also transmit is serial number back to the tag reader. When I get the serial number tag reader take it and send it back to the database, and database basically say that this number is matches, then it's read back to the tag reader, and tag reader go back to the what do you call it, the gate or whatever it's trying to operate that gate. All right. So things that there are two coils. I think there are two coils. One coil from the reader transmit a signal. That signal comes to the antenna of the tag, and that signal should be strong enough to produce enough current to activate the chip if it's a passive. Then the chip will activate and send back that serial number back to tag reader, and tag reader read it and send it back to the database take it and read it, and if it matches, it's gonna take the action, right? So that is passive. If it's active tag reader, that means this tag is active RFID. This tag has its own power, so it does not need a strong signal from the reader to produce enough current by itself. Because tag reader had its own power supply, and whenever is there a signal from the tag reader, is activates its own power and send it back the number to the tag reader. So that means your active tag reader could be in a long distance activity. If you have passive one, it needs to be closer because you need a strong signal from the tag reader to produce enough current into the tag. All right. There are different frequencies over here: low frequency, high frequency, ultra high frequency. The low frequency means your data rate should be lower, right? And ultra high frequency means they have a higher data rate and it would be long distance. All right. So that's all. This is a checkpoint. I'm going to ask you the question in the class. If a TEM, transverse electromagnetic wave, is traveling in the Y direction now, remember we did all for the Z direction, can its electric field have components in X, Y, and Z direction? So if you understand the Z direction propagation, you should be able to answer this question. And also we're going to do the problem in the class. So that's all for the lecture 19. And we're going to get to the lecture 20 in the next video.